The sun is orange, there is green, and the moon is blue. Okay, so this is the simulation. Let me show you the steps. Okay, so it starts moving. As you can see, primarily the primary effect is the moon is the Earth, the green one, starts to rotate around the sun. And now observe what's happening to the moon. What's happening to the moon?
It's getting longer.
And
It's casting shadow on Earth.
that's right. And we call it
The eclipse.
the eclipse. So this is the eclipse, roughly. Okay, so there is a rotation of the Earth around the sun. Okay, that's visible motion of the green dot. And in the meantime, the blue dot is rotating around the green dot. And at some point, it might get in between the two, and in the sight of line of sight from the Earth to the sun, and that's the shadow. Okay, so that's exactly what you're seeing here, and you could go on, and you can see the rotation of the moon around the Earth. So I don't want to go into the details. This is a simulation. It's like the more advanced part of calculus, but what we're looking here at is these functions. First of all, even though you don't see the whole function, you can see that if we each column is a function. Each column is a function, meaning that it produces each column. Well, say what should I pick? How about this one? I pick this column and I pick that column. Okay, so time column and the position of the Earth, the F column. Okay, these are numbers. In what sense does it describe a function? So the first column is what? What? Time, yes, but if we are sort of, try to move from physics towards mathematics, and you have a function has two variables, right? So the first one is what? The independent variable. Okay, the independent variable is time, and the other one is dependent variable position with respect to x, the horizontal motion. Okay, and that is the functional dependence, because the position depends on time, not vice versa, right? So if you know the time, you know the position of the Earth. Okay, so that is a function, and as you plug in the number for the time, you have the output, the position, and it goes through some complicated formula, but that's how it works. From time, we produce a number. We produce a new number, which is the position, the x position. Similarly, you have the y position for the Earth, and then you have x and y positions for the sun and for the moon over there. Okay, so there's a moon there too. Okay, so that's the how function come up, and there's more here because we're talking about rates of change. Okay, so rates of change of the position is what? Let me, it's not exactly here. The rate of change of the position is the velocity. Okay, so how fast your position changes with respect to time is called velocity. And just to refresh your memory, it might look like this. Well, It is based on this very familiar um, formula. Distance is equal to time times
Velocity.
velocity. I'm using the more terminology that is more common in outside of calculus, but once we move to calculus, then it's not speed anymore, but velocity. What's the difference between velocity and speed?
Velocity just goes one way. Speed can be.
No, vice versa. Vice versa. The speed is always positive. It cannot be negative. Velocity tells you not only how fast you're going, but the direction to. Okay, so if I'm moving, and the direction is determined by your axis, so you're moving along the x-axis, for example, then this will be positive velocity. If you're moving in the opposite direction, then it will be negative velocity. So time interval, and this one is called displacement. So once again, we're moving from more elementary situation in outside of calculus, let's just say, and where everything is positive, and then we just decide, depending on the direction, whether to take it positive, take it negative. Well, we cannot stick with that idea anymore because simply we don't want to know ahead of time whether it's going to be positive or negative, just like with motion of the earth. Look at it how we proceeded. So it has been moving to the left, which means that the direction was, which means that the velocity, x velocity over here, x velocity was negative as a matter of fact. But you realize if we keep doing this, at some point it will start moving from left to right. Okay, so to reappear at some point. Okay, so as you can see now we're moving from right to left, which means that the x velocity is positive, and even though the speed is still over there, we can still compute the speed, except the speed is computed now is not only based on x prime, but also x prime, y prime. So like this, x direction and y direction that's combined together gives me the speed. But at this time, this is what we're looking at. We're looking at, we don't want to deal with a problem as complicated as that one. Celestial movements, it is in fact is a way more complicated than that because we have two dimensions only, and well, the third dimension is way more. We know the third dimension. If you know what contribution of the third dimension is to the what does the why is it not flat? This is look at it's flat. It's imagine that the solar system is you imagine you're like God and you're looking at the solar system, blah blah blah, and they're rotating like a table. On the table you have rotations of the planets. Okay, but that's not the case. Well, Matt, yeah.
Down all over the place.
That's right. So sometimes they go up and higher and lower. Even though the sun and the earth behave in exactly that way, the moon is misbehaving. It is actually moving like this. It is going horizontal, vertically as well. So these are two horizontal x and y, like I said, it's a table. But the moon goes up and down. If it was truly like this, you can imagine what's happening if the third dimension we would have eclipse every month. If the motion was flat entirely, if the orbit of the moon was not inclined, we would have eclipses every not we us, but on the Earth. So, well, that's not the case. So the third dimension is not here. We're simplifying it, and it's still a bit too complicated for starting point of calculus. So we actually start elsewhere. We start with, suppose there's only one dimension. Not 3 as we have, not 2 as we see here, 1. Okay, so in other words, what's the analogy of that? It is about driving. So we have a straight line, we're driving, and all we want to understand is, or we're following the area, regardless. That's also a good way to get started, is we want to understand how it moves and how fast, what direction, and maybe solve similar problems, except there will be one-dimensional, and the typical one is what is, well, throwing an object in the air, and at a time we want to know how long it will stay in the air, when it will going to hit the ground, when where it's going to hit the ground, and how far up it goes, things like that. So that's calculus one. We will, and at some point we will later on in the semester we'll do two dimensions a little bit. So because when you throw an object forward, you already have two dimensions. You have vertical and horizontal, so you have to deal with them separately, just almost like this. Okay, so we're going to do one dimensional, and the analogy is probably the easiest one is driving, and the idea is where this formula really comes into effect is whenever you have your okay. Your speedometers work. Okay, so if you have no speedometer, how do you find your speed or velocity? Or you can approximate. You see how?
You set your timer, your odometer,
Yeah.
and you figure out, say, if you want to figure out how long you go in a minute, you'd say, and you travel 1 mile in a minute.
That's right. That's absolutely right. So then what you get described is this formula. Using this formula itself, we move stuff around. We will express velocity, right, in terms of displacement and time interval. Okay. So in other words, 1 minute, say you look at the odometer and see how far you went in 1 minute. Okay, then you multiply the number of miles that you have counted by 60, and that's your speed. Okay, so displacement would be number of miles on the odometer, and the time interval, say 1 minute. That is your choice, right? You could do it if you want to rougher estimate it to 10 minutes or a whole hour if you care, and that's how it works out. Uh, uh, that is the and this is the beginning of calculus. So it certainly you realize that during that minute you might be changing this whole minute you might be changing velocity up and down, and this is not exactly the exact value of velocity, but what we call the average velocity. So it is the velocity averaged over that time interval. Okay, so once again, measure displacement, measure time interval. Or you need the clock and you need the motor. Okay, so that gives us the starting point. This is what the meaning of this fraction is the rate of change. So when you start using the mathematical language um, in place of something that would be more related to physics. So the rate of change of the position or location relative to time or with respect to time. So that is the displacement is the change of, what is the displacement? It's nothing but the change of the position, change of the position. So change of the position, it is displacement just if we were in one word, we say displacement. Otherwise, you take, well, what is it? The display change of position. So position after 1 minute, 1 minute, and subtract position after subtract the current position, right? All Okay, so that is the numerator, and the denominator is the uh, time. If you have a clock, you record. You can record 1 minute, or you can just record time. So time after 1 minute minus current time, and of course that is 1 minute, unless you want to do 1 minute. Okay. Okay, so this is the starting point of calculus. If we want to get slightly ahead of ourselves, what we do is we also what we want to do in addition, we want to, what will come up later on is the problem that we want to go in the opposite direction. So what if your odometer is broken and you want to know your speed? Hold on a second. The speedometer is broken. You use odometer to compute your speed. Okay, what is it? It's the opposite. And suppose the odometer is broken and you want to know how far you went. What do you do?
Speed divided by time.
Say it again.
Speed divided by time.
No, I don't think. I think look at the same formula. The same formula applies. In fact, we don't have to make that. This step becomes unnecessary. This is the formula to find out how far you went if you know your speedometer. So every minute you record the velocity of speed, okay, and then you say, I don't know, you recorded the velocity of no, you don't know, you know your velocity, say you have 60, 65, 75 every minute. So what do you do? 3 minutes, how far did I go? So the first minute 60 miles an hour, the second 65, and then 75. How far did I go? How far did I go during the first minute? It's 60 miles an hour.
1 minute.
1 mile, yeah. So it's 60 divided by 60. Okay, so in other words, you apply this formula multiple times rather than once, as we're going to pursue now. We'll deal with that one quite a bit later with the problem which is reversed. It is reversed from from finding velocity from displacement to finding displacement from velocity. It's once again an order speedometer problem. And as you can see, there will be more addition than anything else. It is easier to see if you just think in terms of if you are time interval, you choose an hour. Okay, if you choose an hour interval, then you need a rough estimate. So you have to do it for 3 hours. Okay, and you don't have a longer. Okay, so how far do you go? You take during just look at the speedometer 3 times during the first hour, second hour, third hour. And then at least 3 hours. That's it. Right? That all it takes. If you do it every minute, you will have a more accurate estimate. But otherwise, you just have 60 plus 65 plus 75. If you do it once a year, and once again, the time interval becomes important. But this is what we're going to pursue. This is just the very first step. The second step will be to find out the instantaneous velocity. Okay, so not the average velocity, which is okay for approximation of how far you have driven, or rather how fast you were driven over some period of time. But you know when instantaneous velocities are important, that this is where the accuracy is paramount. Well, this is one example. You can imagine how accurate it should be so that they can predict the eclipse within a minute or less. In fact, it's within seconds. So then the accuracy of this kind of approximation is not useful. So what you do is then you have to know, you have to solve these problems with absolute accuracy. And that is done by, and we're going to do it when time intervals, we'll let time interval go shorter and shorter and shorter and shorter. and then we see what happens to that fraction. So if time interval gets shorter and shorter and shorter, the displacement is also gets smaller and smaller and smaller. So in other words, we end up with numerator going to 0, denominator going to 0. We call it the limit because those techniques that we learn will allow us to evaluate these to 0 divided by 0, which is quite a quite an expression that it certainly has more meaning. So it's not division by 0. So 0 divided by 0 is not 1 divided by 0. 1 divided by 0 is division, but we know it's bad. Okay, but it's not as bad as 0 divided by 0. Okay, so we'll have to deal with that later. But I want to break these problems into two steps. So we first understand the rates of change, velocity at the rate of change, and secondly, we will look at the limits. Okay, so so the starting point will be then will be sequences. As you can see, this is, I mean, the assumption is naturally when you look outside that the sun is moving continuously. So if it gets from this point to that point, it does not skip any points in between. But that is a challenge. That is what you need the calculus limits for to resolve. But you could do approximations nicely with nothing but sequences. These are sequences. As you can see, in fact, if you look at the column, this column over here, this gives you the number of steps. So I have carried out 393 steps. And it is jumping. There is nothing in between. This is it's not computing. This does not do any calculus. What it does is well, from the physics of the problem, we figure out the acceleration. Those two columns, okay? From the accelerations, we figure out velocities, and from velocities, we figure out the position. So this step, we just discussed. This is what we just discussed. We know the velocity, and you want to know find the position. That's how we do it. The formulas are very simple as that. So let me just show that it is indeed the case. Say x position. I'm not sure if you can see this tiny formula over here at the top. So how the next position, this one, the next position of this object, this time the sun, what happens to it, or if we know its previous position, right, the blue square above, okay, this is the previous position, this is the next position that we're trying to find, and we know velocity. So how do we find it? We know velocity, and we know the previous position. What's the next position? Well, look at the formula. Can you see it at the top? Or it doesn't reflect when you ride the lights? No? So can you see this formula over here? This is the formula. It is really tiny.
The next position will depend on the speed.
On the speed, yes. So it would be the previous position plus
the time that you would take it at.
Yeah, that's right. The time is here, by the way. I forgot to mention. This is the time. The time interval being very small, so that we could see slow progress. And as you can see, this is the formula. So you can actually see these two highlighted squares. The previous position, r minus 1c. That's the previous position. R refers to previous row, r minus 1 previous row, and c refers to same column. So previous row, same column, one step up. And what we add what we just did add. We add velocity multiplied by time. So we're at a time, the red one, multiplied by the velocity in the purple one. So the blue previous position, or current position, we add to it the velocity multiplied by time. And we find the next position. That's the whole thing. Okay, so this is a pretty nice simulation, but it is based entirely on this very, very simple computation. Okay, so most of the projects that we will get to later will have something like that in a similar setting in nature. So it's about motion, it's about computing locations from knowing velocities or acceleration, as in this case, and that's what we have here. So as you can see, it works out very elementary manner. But if we do it with two dimensions, they're interacting a then the complexity of what you can accomplish is quite remarkable actually. I forgot to demonstrate you what happens if we if we increase the size of the Earth. I picked random numbers for the Sun 500, for the Earth 1, but as you can see, let's pick the Sun much larger than the Earth. Okay, so if I make the mass of the Earth larger, what is going to happen? If you can guess. So if I give it 500, what kind of behavior? What kind of behavior will happen? Two objects attracting each other.
Will they hit?
Almost. I mean, they would hit, but you see, as you saw, the initial position or the initial velocity of the Earth, the green one, was out. So they are not moving towards each other. The moon is moving in a kind of perpendicular direction. So what do you think is going to happen? So the Earth is of the same size as the Sun.
Probably more oblique, oblong, orbit.
Ask yourself what's going to happen to the Sun. What's going to happen to the Sun?
All these stars rotate around each other since it's the same size.
Right. Yeah. Pretty much. Well, let me demonstrate. They will be starting rotating around each other. The number one observation, what you're implying, is that the Sun starts moving. It's not moving only because the Earth is so small, too small to pull it off its position. But now it's gonna start moving. So let me show you. See, it's starting to move. The moon is gone. Finally, it's totally gone. And now here it is. They are dancing around each other. Well, I mean, they are dancing away, unfortunately, so out of the screen. But you can see what the picture on the right is taken from the position of the Earth. So what we would be seeing, and there indeed it seems like what's his name was. Look at it. The Sun is rotating around the Earth. Well, so anyway, the behavior will be very complex. Very complex when we cannot ignore which we did initially, the pull of the Earth onto the Sun. So the Sun remains fixed, and that's why we have this nice picture. Sun stays in the middle, the Earth rotates around it, the Moon around the Earth. And once again, the Moon is so small that it does not pull the Earth off its orbit. Then we have this nice picture that I tried to show you. But once they become bigger with respect to each other, they have it goes well.
Will they eventually hit, or will they eventually slingshot each other?
They totally might. You see, what they are rotating around is not each other. They are rotating around the center of mass, and they might continue to rotate. But they might start converging onto each other, and then they meet at the center of mass. That was me. Was that these are sequences. So the sequences really give us a lot of flexibility in modeling. We can model motion in a very profound way, and based on this one is pretty much based on physics, and although the data is not realistic, but it produces a picture that is realistic somehow. So that's what we're studying sequences. So any ideas of what we're talking about? So the sequences are literally sequences of numbers. So these are numerical sequences. Okay, so 1, 2, 3. That's a sequence. Okay, so the simulation that we just saw, the only difference is that you have two sequences at a time, one for X, one for X. But otherwise, it's still a sequence. They usually exhibit more complex behavior than that, but this is what we're going to be studying for a short while. What happens to sequences, especially long term. So as you can see, they're simpler than functions. They are functions, but of a simpler kind. Okay, so here's another one. Half, 1/3, 1/4, 1/5, 1/6, and you can ask yourself, what is the trend? The trend that's called the limit. So we'll start by describing them in a more informal way, and then we will make it more precise. So how do we describe the trend of the first one? What? Okay, well, it's not the trend. What you're saying is the pattern. It is the pattern is indeed add one. Okay, so that is helpful once we want to establish find a formula for it. Okay, and what you just described, let me just take it. It is in fact called recursive definition. Okay, if you look at the name of the file over there, this is recursive. So once again, we know our current position and nothing else. We don't know the past. We don't care. As you can see, I have only two rows used for each of these. So we don't know anything about what has happened in the past. We only know where we are right now, and we know our velocity. That's enough for us to find where we will be the next moment. Okay, so that's the recursive definition. This one is especially simple. We just add one. Add one is the recursive definition. So well, we discuss this slightly later. And the recursive definition for the second will be more complicated. In fact, it's not really very productive. So let me just let's get to this in just a second. What are the trends? Trends as we go on and on, as we continue. Remember what if you have seen this before, those dot dot dot, what do they mean? They mean that we go on forever. We keep writing those, even though we don't happen to make time. That's why we cannot finish the job. But we imagine that we do it. As long as the pattern is clear, and it is, right? We should be able to figure out what's happening. So, what's the trend? Oh, the first one. What?
It will increase until infinity.
Right. It goes to infinity. That's right. That's the whole thing. So this is the most important feature of the sequence is that it tends toward infinity. What about the second? It trends towards zero. So these are two things that we call limits, and we also in the former case it is the infinity, in the latter case it is zero. And we're going to be studying them, but before we actually get to that, we'll talk about the sequences in general. And recursive sequences are the most typical. So once again, examples are position, the next position for the current. So here's an example. Next position from current. That's one example. Another example is similar, except we're not measured not in the in say miles, but measured in say dollars. So another example would be what happens to your bank account. Okay, the simplest case is I start with the simplest case of what's happened to your bank account if you add $100 every month. So once again, you have a recursive behavior. So you know if you know how much you got today, you will know how for this month. You will know how much you got in the next month, and so on. We can compute everything. A more complex example is what's more complex behavior in banks? Interest, right, so add, say, 5% interest every year. Once again, if you know your current amount, by following this rule, you find the next amount. Okay, so we'll continue this next time with more examples. Read the syllabus again and let me know if you have any questions. Definitely, you have to get started with the orientation. Yes, soon as possible.
Now, when's the first show homework?
Friday night.